Hello students, so continuing our lectures on thermal spray, uh, we'll start with arc spray today, or arc plasma spray. Now in arc plasma spray, the arc is basically transferred. So we have a transferred arcs, and it acts, and there is a workpiece on which the arc is being produced, and this workpiece is the anode, and it is similar to the welding process. And we have localized fusion, and we get metallurgically bonded deposits. Oh. In what do we have in arc plasma spraying is the powder is feeded, this is the precursor, and we have a high velocity gas, and we sort of use a plasma torch and the gas is basically nitrogen and oxygen and atmosphere. And so we have a plasma frame generated here. And like other cases, from the nozzle, this is the nozzle, like other cases, molten particles are ejected out and they are deposited on a substrate. Now here the gas which is used, it is ionized, and it leads to a plasma jet. And careful nozzle design is required in this case. It's required for to stabilize the arc for continuous operation. And mainly you have, as I have already told you, mainly you have nitrogen, oxygen, as well as argon, and little bit small addition of hydrogen is used as the gas. So the process involves energy transfer from plasma. So there is an energy transfer from plasma jet to the particles. Plasma jet to particles. This transfer is very efficient in this case. Now, the disadvantage associated with plasma spray is the interaction between the molten particles atmosphere. Interaction between molten particles and atmosphere. So that is why we may switch to, instead of this was an atmospheric pressure plasma, so this A stands for atmospheric here, where we are using nitrogen, oxygen mainly, a little bit of argon and hydrogen also. But due to this interaction that might take place, we need to shift to something called vacuum pressure plasma. So this interaction can be minimized in vacuum pressure plasma. Apart from vacuum pressure plasma, there are other types of plasma like induction plasma spraying, where we have a radio frequency plasma. It is clean with no contaminants from the electrode. Contaminants from electrodes. And compared to its, we could have used the DC plasma also, but compared to its DC part, the plasma volume is larger. Plasma volume of RF is greater than the DC. Now this is about plasma spraying. There are other ways of depositing films, depositing coatings, which comes under thermal spray. One of the significant method is called laser spray, where the laser, this is basically the heat source, monochromatic light, and mainly CO2 laser is used, laser spray, and can be used in any atmosphere, in vacuum or in air also. and we get coatings free of contamination. The most significant or the most in current use thermal spray method is called the cold spray method. So from the name cold is due to we are mainly focusing on the velocity, or the gas velocity is dominant in depositing the coatings rather than the thermal or the heating part. The gas velocity is the dominant part in cold spray. So what do we use is we have a compressed gas, which is basically supersonic jet. So compressed gas is so much compressed and that it forms a supersonic jet when released, and this is disallowed, and this is where you have the feeder, the powder, and a little small amount of heat also, not as in the previous cases, and you have a detonation gun nozzle, and the temperature is, interestingly, the temperature is less than the melting temperature of the feeder. So this is very uncommon, because in previous cases you need to have a molten system to allow the material to get deposited, but here the temperature is kept lower than the melting system. It is the supersonic jet which actually causes the coating. So coming to its basic features, we have something called plastic deformation taking place at the substrate. So since we are using a low temperature melting system, so the coating basic mechanism comes from this plastic deformation, and so it's much lower temperature than the previous cases. And we are getting shock waves due to the supersonic jet at the substrate, and these shock waves they are the reason to cause this plastic deformation. So what happens is that the feeder is basically a mixture of there is always some metal part associated with the feeder. The mixture of a metal and a ceramic. So if it is only metal, then there is no problem, but if we are depositing a ceramic coating, then also at least 10 to 12% of the feeder must contain a metal part. For example, tungsten. So this metal part is the reason that the shock waves will cause the plastic deformation. So this is the reason for the material to get adhered to the substrate. And there are some disadvantages, or there are some deleterious effect associated with cold spray. Like can have high temperature oxidation, can have evaporation, there can be melting, There can be crystallization. Apart from that, you can have residual stress. Have something called debonding. And there can be gas release as well. These are some of the negative effects cold spray can have. Now, if we now, what are the advantages that we get apart from this the deleterious effects? Advantages associated with cold spray are so it's right here. Cold spray advantages. We can have high hardness. Since it is a cool welded microstructure. Can usually has a lower shrinkage on loading. It can have high strain on impact. Then, since it is a low temperature process, so there is no bulk particle melting, no bulk particle melting. And it retains the composition. So composition is retained from the initial metal, and that means the initial phases are maintained. Initial phases present in the feeder material are maintained, and there is very little oxidation. This also comes under since we are using a low temperature. Had it been a high temperature, it would have caused high oxidation. So we are using low temperature, so very little oxidation is involved in cold spray, and disruption of oxide on impact. And even if there are some oxides formed, there is a disruption of oxides since due to the shock wave generated on impact. These are the advantages. Now, if you plot all the cold spray techniques that we have discussed, you will do the plot in terms of temperature. So here is temperature, it's in degree centigrade, and we put the velocity of the gas is in meter per second. So the different techniques will take up different places in this chart. Like the lowest one will be your cold spray that we have discussed right now. So this stands for the cold spray technique. You can have arc technique somewhere around here. your arc. Then below that there will be powder technique, powder flame spray. Below that there will be wire flame spray. And sorry, okay, this is okay. Here this is the plasma spray. Technique here. And the D gun comes here, detonation gun, because in this case we are going to the high velocity, and HVOF comes here. The extension of this is much more. So you can see that the best method at present is the cold spray technique, and if you plot the temperature, this is around 300 meter per second, and this is around 1200 meter per second, and the temperature here is 500 degrees centigrade and to 5000 degrees centigrade. And cold spray technique, you can see that we are more towards using a very low temperature compared to its melting point, but our main focus is on the velocity of the gaseous material around here.